we were talking of the effect of grain boundaries on strength. As I just told you that now in the next few slides, this lecture, part of the next lecture and so on, will be the effect of plastic deformation on normal metals. Normal metals are polycrystalline, which means that in normal condition they have thousands and millions of crystals inside them. Now, just because we have not covered the chapter on crystals, but crystals are very small shapes of standard sizes, and the boundaries between the crystals, are called grain boundaries. The boundaries between the crystals are called grain boundaries. So for us, that is it. That is the important thing for now, that we don't know crystal structure. We have shown you that some are BCC, body-centered cubic, some are FCC, face-centered cubic. So those are special shapes, and those metals have crystals of only that special geometry. But just like anything, crystals are small shapes. So they are touching each other, and where they touch, that area is the grain boundary. Now you will see another technical term here, dislocation. Dislocation. So we will cover a chapter later on which is about defects at the crystal level. Defects at the crystal level. So dislocation is a type of defect we will see at that time. So two things we are talking now, which we will actually cover in detail in later, that all metals are made of very small crystals. Where the crystals touch each other, that is called a grain boundary. That is one part. The other is that at the crystal level, there are certain defects and flaws in the material, and one of them is called dislocation. Dislocation. Now, what we want to know right now is that, okay, when we do plastic deformation, you see, when there is a metal, you apply load, nothing happens. You apply more load, nothing happens. After you apply a certain amount of force, it starts to deform. But then when you remove the load, it goes back to zero deformation. So that area is the elastic part. When you increase the load so much that it deforms, and when you remove the load, it does not go back, it is now plastic deformation. This we know. So when we apply load, the material is deforming. How does it deform? How does it change shape? The material, whatever material is, it leaves its place and goes to some other place, isn't it? So that it bends. It was a straight line. It was a bar of a straight line. You applied load, it bends now. So it bends mean that some material has left its original position and gone to some other position. So deformation means that some particles of the material have gone to a different place. So similarly, there were some dislocations inside. Some small flaws, some small defects at the crystal level size, nano level size. So when we move the material, when it deforms, these dislocations also move. So this is how deformation takes place. When a material is deformed plastically, then the dislocations move. But now there is something that when a dislocation comes and hits a grain boundary, then it cannot move any further. It is stopped by the grain boundary. This is what happens inside the material. Dislocations move when you apply enough force to deform the material. Dislocations keep on moving, but when they hit the grain boundary, they stop. So now they cannot move. So it means that grain boundaries resist deformation, right? Because movement of the dislocation is a proof that the material is deforming. And when it comes to a grain boundary, it stops. So now the dislocation cannot move any further. It means that the grain boundary is a resistance of the material to further deformation. Therefore, we say that grain boundaries strengthen metals and alloys. They increase the strength of metals and alloys. Right? So this is a major discovery. It is a major thing, that if it is a polycrystalline metal, there will be hundreds and thousands and millions of crystals. At the boundary of each crystal, there will be something called a grain boundary. Because these grain boundaries stop dislocation movement, So grain boundaries are a resistance to the deformation of a metal. Therefore, we can say that if there are more grain boundaries, the material is stronger. The material is stronger. Okay. Now, what is fine grain size? Grain means crystal, right? Grain is another word for crystal. If there are many crystals, each grain is small in size. If there are a few crystals, each grain is large in size, right? This is very simple. So, if there are many grains, then we will say that the material has a fine grain size. Fine grain size. We understand, right? That if there is sugar, if there is salt, when it is very fine, the particles of the sugar are very small. If it is coarse, C-O-A-R-S-E, coarse, then it is not fine grain, it is large grain sugar. So here also, if there are many crystals, each crystal is a small size, then we say it is fine grain size. Now we say fine grain size is desirable. Why? You see, we are saying that grain boundaries increase the strength of the material. Grain boundaries. If there are big particles, big grains, then there is only a few grain boundaries, sorry. But if there are many hundreds and thousands of small grains, then there are lots and lots of grain boundaries. Do you understand? Let me repeat. If there are only 5-10 grains, then there are grain boundaries for only 5-10. But if there are a million grains, then each grain has a grain boundary. So there are millions of grain boundaries, right? So fine grains mean more grain boundary, and grain boundary increases the strength. So therefore, fine grain size increases the strength. So this is a brand new piece of information for you. When we will go into the crystals chapter, we will cover it more. But right now, it is the same material. It is one type of steel or it is one type of aluminum alloy. It is the same material. But when we process it, when we manufacture it originally, then if we can control the size of the crystal, the size of the grain, then we can change the strength of the same material. Do you understand? This is remarkable. Normally you feel that one material has one strength. But here we are saying it is the same material, but because it is a metal, it will be crystalline. And if we, in the manufacturing technique, if we can control the size of the crystal, if the crystal size is large, it will have certain strength. If we can reduce the crystal size to small, so that in the same 1 kilogram there are many more crystals, then there will be more grain boundaries, and more grain boundaries will mean that it is stronger. So fine grain size is desirable, and therefore metals are produced with fine grains if we can. In general, fine grained metals, metals which have a lot of crystals at room temperature, the advantages are they are stronger and harder. We told you just a little while ago that if the strength is high, hardness will also be high. So these two go together. Because of a lot of grains, there will be a lot of grain boundaries, and grain boundaries increase the strength. So for fine grained metals, they will be stronger and they will be harder. This is a bonus. They will be tougher also. We told you that normally if strength is high, it is not necessary that toughness will be high. But if it is fine grained, then the toughness will be high also. Also, they can be strain hardened. Remember, when we were discussing the stress strain curve, there was an area between yield strength and ultimate strength, which we called a strain hardening area, where if you do plastic deformation and remove the load and then use the material again, its strength is increased. So materials with fine grain can also be strain hardened. Also, their properties are more uniform everywhere, not here, everywhere the property is the same because they are fine grained. This is called isotropic, if you remember. Isotropic is a word that in every direction it is the same. Isotropic, in every direction it is the same. So they will be stronger, harder, toughness would be good, they can be strain hardened, and their properties will be uniform and isotropic. These are the advantages of having fine grain. But in the world, nothing is only good. Many good things are there, with it some bad will always be there. So what are the disadvantages? If they are fine grained, their resistance to corrosion is low. Resistance to corrosion is low. And creep is something, creep is a word, deformation under constant load at higher temperature. You see, if the room temperature is there, then creep usually does not happen. But if we apply a load and keep that load applied, for example, look at any building. The weight of the building is always there. So on all walls and all columns and so on, the weight is permanently there. So this is not a weight which will be gone. This is a load which is permanently there. So when a load is acting permanently, then what happens is called creep, especially when the load is acting permanently and the temperature is high. So during summer, when the temperature is 40 plus and 45 plus, then the creep on your concrete structures is more, right? So that is called creep, deformation under constant load at higher temperature. So the resistance of the material to creep will be low, and the resistance of the material to corrosion will be low if it is fine grained. So there are all these advantages, but these two are disadvantages with fine grain size. So effect of grain boundaries on strength. Effect of grain boundaries on strength. If there are more grain boundaries stop dislocation movement, and therefore they increase the strength of the material. So this is the effect. And grain boundaries will be more in size when there are fine small grains. So when we say more grain boundaries, we say fine grain size, right? So this is important. So you have learned a lot of new things right in this one slide. Here they are just showing, right, same material, but this graph is for the single crystal material and this graph is the polycrystal. Single crystal will be made by very, very special manufacturing technologies. We don't know normal technologies, but here is the tensile stress, the ultimate strength in PSI and in megapascal region. It is the same material, but you see that the stress strain curve is much higher for normal polycrystalline compared to single crystal. Single crystal will have some very special optical properties and magnetic properties, but in terms of mechanical strength, it will be very, very low. So therefore, usually in normal mechanical products, we have normal polycrystalline materials, not single crystal material. Okay. Here we have an equation. Two scientists, Hall and Petch, together discovered this law. So it is called the Hall-Petch equation. This is the equation. Sigma y is the yield strength. Sigma naught is some constant strength number, reference strength, and K is also a constant of the material. A small d is very important here. It is the average grain diameter. Average diameter of the crystal. So you see, yield strength is inversely proportional to grain dia. Do you understand? And if you square this, because this is the root, right? So there is a square type of relation here. So if you decrease the dia, yield strength will increase. If you decrease any number in the denominator, the total value increases, isn't it? So when you decrease the grain size, the yield strength increases. So this is an equation which confirms what we just said, that fine grains increase. Because of fine grains, which means a small grain dia, there will be more grain boundaries, there will be more strength. So this is now an equation, right? This is now an equation. Of course, the constants sigma naught and K should be known for a given material. But this Hall-Petch equation then tells you mathematically as an equation the same thing that you studied in the previous slide, that when it is fine grain size, the average diameter of the grains is small, then the strength will be high. So we will stop here for today. We will continue inshallah. Thanks a lot for being with us. Ma'as salama.